Now we can define E, and it always helps to remember definitions. The goal, as always in this class, is for you to be able to use your normal brain and just to think of these as complicated topics, but not having a special subject, but just one that you can think through. The number E can be defined in one way as this figure. It's a number slightly larger than 1 plus a fraction that's raised to a power. And it's the product of raising that number n bigger and bigger until you get as big as you want, until you get a close enough approximation to what n would be if it went all the way to infinity, close enough approximation for that to be useful. And it turns out that E remains a very small number. It's even less than 3. It's 2.7 something. Even though it's raised to a very large power, because as the power gets bigger and bigger, the number raised gets closer and closer to 1. So just to unpack the parts of it, here's one. We have this little fraction. And you should be able to recognize a similarity to the compound interest formula, where we've got that figure in between parentheses, 1 plus a small fraction. That could be a rate. Our 5% rate or 2% rate, some small fraction. Now, as n gets larger, of course, the whole fraction gets smaller. That's how fractions work. And as that fraction gets smaller, then 1 plus that fraction gets closer to 1. That's fairly obvious. If you're adding something to 1 and that gets smaller and smaller, then the total gets closer and closer to 1. So that's as that number n gets bigger, that's one direction in which the whole figure, and therefore the whole value of n, goes. It gets closer to 1. We're not done yet. It doesn't remain 1, but we get closer to 1. But now, as increasing n has this tendency to make the whole smaller, it also has a tendency to make the whole larger. So we're raising something to a power, and we're making the power bigger and bigger. And of course, exponents have the power in the common sense to make things very large. The number 2 raised to a large power becomes a huge number. At 8, it's already 256, and when the power 2 is raised to gets very large, then that tiny number 2 can become something very large. So this is something very familiar with us. N gets larger. As long as n is greater than 1, the number gets big and bigger. Now, of course, if the number is equal to 1, we're raising it to a power, then it doesn't matter what the power is. It's going to stay 1. You can multiply 1 by itself as many times as you want. You won't get anything other than 1. So what do we get? Well, as we're approximating E, we get a better approximation if we make that number n larger. And as we make it larger, our approximation for E is pushed in 2 directions. The n in the denominator of the fraction, as that gets bigger, it makes the number raised to the power smaller, and the n, which is the power, as that gets bigger, it makes the whole number bigger. And the compromise between these two, the balance, is something like this small number. That's as big as E gets, no matter how large how large you make n. We could make it more precise by adding more decimal points where I've just put ... But it would never get bigger. No matter how big we make n, it would never get bigger than 2.71829. So all of this is just to help you get familiar with E, and of course much of the difficulty of mathematics is a mere appearance, because things seem unusual and hard to think about, but they often have simple and clear meanings that are well within your capacity to understand. So E is in fact nothing scary. It's just a number very much like pi, not too different in value from pi. And since you've been dealing with pi since you were a child in school, there's no reason you shouldn't be able to handle E as well, especially since it will make the problems we've already been doing rather simpler. So I've just been trying to explain E on its own, and I'm not going to go all the way of trying to show you step by step how E helps to solve compound interest problems, but I want to give you a sense of why it's relevant, so we can look back at our compound interest problems. And this, we might say, is the formula we've been dealing with to calculate compound interest. You take a certain amount of principal, and in order to figure out what becomes of it if it's invested over time, then you have to do some calculations involving raising a figure to an exponent, to a power. What is that figure? Well, it's 1 plus a small fraction. And we've gotten used to, through the last set of homework, we've gotten used to making these calculations. What do you do to figure out a compound interest? Well, you have to work out this fraction, that you take a percentage which implies a yearly rate, which gives a yearly rate, and you have to divide it up if you're going to use compounding periods from a shorter time. So in order to figure out how your interest will compound, you have to figure out how much interest you have in each compounding period. If you want to compound every year, then you can go with the yearly rate. If you want to compound every month, then you have to divide it by 12 to find out what you earn each month. And you can go daily or for even shorter periods of time. And you have to slice up the annual interest rate to make it smaller and smaller, because you're earning that rate over a shorter period of time. But then when you increase those periods and you lower the interest rate, then you raise it to a higher power. If you're figuring out an annual compounding rate, then you can use the annual rate directly in your compounding formula, and the number of years itself will be the power. But if you're using shorter periods, then you have to lower the rate and increase the number of periods, right? And this should remind you of how we derived E. This is the relevance of E. It somehow does the hardest basic math of this once and for all. If that abstract description I just gave is a little confusing, let's just remind ourselves that we went through it step by step in a way that wasn't too difficult to understand. This would be the formula for our annual compounding with the example we're using. $200 invested at 5% per year, 5 divided by 100, for 4 years, and it gets us this amount. If you want to compound monthly, then you increase the denominator in the part of your formula that records the interest rate so that the rate gets smaller. You're earning generally at the same rate, but you're investing for a shorter period of time, and therefore you get less money. But then you end up with ultimately even more money because you count more of those periods. 4 times 12 months is 4 years. So if you've lowered your rate by a 12th because you're compounding it 48 times, you get an extra $1.08. And this pattern continues. So if you want to go daily, then you do what you did in the case of monthly, but then you add the 30 days. You make the interest rate even smaller because you're considering what you earn in each day of that year, taking 360 rather than 365 as the days in the year. And then you increase the number of periods. And so we see that what happens is what we understood to be happening with E. As we increase the number of compounding periods, that's increasing the number n as it was when we were talking about E, and it makes the number raised to the power closer to 1, and therefore the ultimate number smaller, but it makes the power larger, and therefore the ultimate number bigger, and the compromise between those two doesn't go down to 0, and it doesn't run off to infinity. It becomes a tidy number so that we can see when we get very precise, we're compounding now every hour. It's as though you had an accountant sitting at a desk all the time, constantly calculating the money you're making. Every hour on the hour, this accountant will take out a calculator and figure out how much you've earned so far and add to the principal and let that amount influence how much you'll earn in the next hour. For all that trouble of being very accurate down to the hour, you don't even earn as much as a full penny over the course of 4 years. That could be significant with higher rates or higher principal. But when you learn how to solve these problems accurately, even for trivial amounts, then you can also solve problems that involve the same mathematics when the continual compounding does actually make a difference. So to go from compounding every hour to compounding every instant, you have a somehow magical accountant who can already be accounting for how much interest you've earned before he's done calculating how much interest you earned before he's already started calculating how much you will earn in the future. Every tiniest bit of time, your investment adds to its investment, and all those tiny bits are allowed to increase your overall wealth. So far, it's not helping you very much. Got 2/10,000ths of a dollar over the course of 4 years, but we are getting the accurate number. And the thing to realize here is that the structure of E, that definition of E, is something that we're in fact familiar with because it's a thing that comes out of problems that we were already working on.